What are the different types of current transformer? Decoding the current, a comprehensive look at current transformer types. Current transformers, CTs, are indispensable instruments in electrical power systems, acting as sensors that provide a scaled-down, manageable replica of the primary current flowing in a circuit. This allows for safe and accurate measurement, control, and protection. Given the diverse requirements of electrical installations, current transformers are manufactured in various designs, each tailored to specific applications and operating conditions. Broadly, these crucial devices can be classified based on their construction, voltage and insulation levels, and their intended application within the system. One fundamental way to categorize current transformers is by their construction, leading to three primary types: wound, bar, and toroidal, or window. The wound type current transformer closely resembles a conventional transformer in its construction. It features both a primary and a secondary winding meticulously wound around a magnetic steel core. This design is versatile and commonly employed across a range of current ratings. In contrast, the bar-type current transformer simplifies the primary winding significantly. Here, the primary conductor itself is a solid bar passing through the core. The secondary winding is then wound around this primary bar. This robust design is particularly well suited for applications involving high currents, where a solid conductor minimizes losses and can withstand significant electromagnetic forces. The third construction type is the toroidal, or window type, current transformer. Characterized by its donut-shaped, toroidal, magnetic core, this CT operates by having the primary conductor, which carries the current to be measured, simply pass through the central opening or window of the toroid. The secondary winding is then wound around this core. Window-type CTs offer ease of installation, as the primary circuit doesn't need to be broken. The conductor is simply threaded through the window. Beyond their physical construction, current transformers are also classified based on their voltage level and insulation type. Low-voltage current transformers are designed for use in circuits operating at lower voltage levels, typically found in distribution networks and industrial applications. Conversely, high-voltage current transformers are built to withstand the stresses associated with high-voltage transmission lines and substations, requiring more robust insulation and construction. The insulation type further differentiates CTs. Dry-type current transformers utilize solid insulation materials and do not rely on any liquid insulation. These are often preferred in indoor applications where oil leakage or maintenance concerns associated with liquid insulation are undesirable. All-type current transformers, on the other hand, employ oil as both an insulating and cooling medium. The oil helps to dissipate heat generated within the transformer, making them suitable for high voltage and high current applications where significant thermal stresses can occur. Finally, the application for which a current transformer is intended dictates specific design and performance characteristics. Metering current transformers are designed for high accuracy over a wide range of currents, ensuring precise measurements for billing and energy management purposes. They are typically used in conjunction with various types of electrical meters. Protection current transformers, in contrast, prioritize accurate representation of fault currents, often at levels significantly higher than normal operating currents. Their primary role is to provide signals to protective relays, enabling the swift isolation of faulty sections of the power system. Summation current transformers serve a specialized function, designed to sum the currents from multiple phases of a circuit. This summed current is then used as an input for specific relaying applications, providing an overall indication of system loading or fault conditions. In conclusion, the diverse types of current transformers available reflect the varied demands of modern electrical power systems. Whether categorized by their construction, voltage and insulation levels, or their specific application in metering, protection, or summation, each type plays a critical role in ensuring the safe, reliable, and efficient operation of electrical grids and industrial installations. Understanding these classifications is fundamental for selecting the appropriate CT for a given task, guaranteeing accurate current measurement and effective system protection.